Debugging kernel modules presents a highly specialized and unique set of challenges compared to typical user space application development. Within the kernel environment, developers inherently lack access to standard C libraries like libc, and traditional user space debugging tools are completely non-functional. Furthermore, the inherent criticality of kernel code means that even a minor bug can lead to catastrophic system instability or a complete kernel panic, demanding meticulous precision. This session will meticulously explore two fundamental yet powerful approaches for diagnosing issues within your kernel modules: printf for efficient, non-interactive logging, and the potent combination of remote GDB with OpenOCD for interactive, step-by-step code analysis. Mastering these distinct techniques is absolutely paramount for ensuring the stability, security, and optimal performance of any kernel-level code you develop, enabling robust system operation. Printf function serves as the Linux kernel's fundamental and most ubiquitous logging mechanism, acting as its equivalent to the printf function found in user space. However, printf operates exclusively within the kernel's privileged environment, necessitating careful consideration of its usage. A key distinction is its implementation of distinct log levels, ranging from kern emerge for critical system-wide emergencies to kern debug for verbose development time information. These 8 predefined log levels are prefixed to the message string, allowing the kernel to classify the severity and urgency of each message. This classification is vital for filtering messages, helping administrators and developers quickly identify critical issues without being overwhelmed by less important debug output, thereby providing a structured approach to kernel event monitoring. Printk: all messages generated by printk are efficiently stored within a specialized data structure known as the kernel ring buffer, a circular buffer residing in kernel memory. To access and review these buffered messages from user space, the dmes command is indispensable. Dmes offers powerful filtering capabilities. For instance, you can retrieve only error messages using dmes-l error, or search for specific module output with dmes pipe grep my_module. Furthermore, the visibility of printk messages on the console can be dynamically controlled by adjusting the console log level via the /proc/sys/kernel/printk file. This tunable parameter consists of 4 values: console, default message, minimum message, and boot time default, allowing fine-grained control over what level of messages are displayed during operation, thus ensuring clarity and focus for debugging. While printk is an invaluable tool for initial diagnostics and logging, it inherently suffers from significant limitations that can hinder complex debugging efforts. Primarily, printk is non-interactive. It merely prints messages, offering no capability to inspect variable states in real time, modify program flow, or step through code execution line by line. An excessive number of printk calls can easily flood the kernel log, making it incredibly difficult to pinpoint relevant information amidst a torrent of output. Furthermore, the insertion of numerous printk statements can inadvertently alter the precise timing of code execution, potentially masking or even introducing new bugs, a phenomenon famously known as the Heisenberg effect. Finally, printk messages have length constraints, meaning complex data structures or lengthy strings might be truncated, obscuring crucial details needed for problem resolution. To overcome the limitations of printk, we turn to the immensely powerful combination of remote GDB and OpenOCD for advanced kernel module debugging. GDB, the GNU debugger, is a venerable command-line debugger renowned for its versatility across various programming languages and architectures. OpenOCD, short for Open On-Chip Debugger, is an open-source tool that provides crucial on-chip debugging capabilities, including in-system programming and boundary scan testing for embedded systems. Together, GDB and OpenOCD form a robust, interactive debugging solution. This allows developers to set breakpoints, single-step through kernel code execution, and inspect variables in real time on a remote target system or embedded device. This interactive control is indispensable for diagnosing complex, hard-to-reproduce issues that printk simply cannot address effectively. Properly configuring GDB is the foundational step for successful kernel module debugging. Firstly, the Linux kernel itself must be compiled with debugging symbols enabled. This is crucial and typically achieved by setting config debug info equals y and config frame pointer equals y in your kernel configuration. These options ensure that GDB has access to source code information and accurate stack traces. Next, a well-structured .gdb init file is essential. This file, residing in your home directory or the project root, should load the uncompressed kernel v-linux image, which contains all the necessary symbolic information. It also defines source code paths, allowing GDB to display the relevant code during debugging. Finally, you will use the GDB command target remote port to establish a connection with the OpenOCD server, which acts as the intermediary to your hardware target. Setting up OpenOCD is pivotal as it acts as the critical bridge between your debugging software, GDB, and your target hardware, often an embedded system connected via a JTAG or SWD interface. The configuration process involves specifying two primary elements. First, the JTAG/SWD adapter you're utilizing, and second, the specific target CPU or board you intend to debug. Common JTAG adapters include inexpensive bus pirate devices, more advanced FT232-based solutions, or professional dedicated debug probes like Seger J-Link or ST-Link. To launch OpenOCD, you typically execute a command similar to OpenOCD-F interface/jtagadapter.cfg-F target/target-cpu.cfg. Upon successful initialization, OpenOCD will listen for GDB connections, usually on TCP port 3333, making it ready to facilitate the interactive debugging session. With OpenOCD successfully running and connected to your target hardware, the next step is to establish the crucial link from GDB. First, confirm that OpenOCD's console output indicates a successful connection to the target and that it's awaiting GDB connections, typically on port 3333. Then, within your GDB console, you initiate the connection using the command target remote:3333. Upon a successful connection, GDB will often pause the execution of the target CPU, giving you complete control over its state. Immediately after connecting, it is imperative to load the kernel symbolic information by typing file v-linux into GDB. This command makes all kernel functions, variables, and data structures visible and navigable. You can now interactively debug, setting breakpoints with b function name, single-stepping with n or s, and inspecting variables with p variable name, offering unparalleled insight. Beyond basic stepping and variable inspection, GDB offers a rich suite of advanced techniques that are particularly powerful for complex kernel module debugging. To delve into memory contents, commands like x/nx address, e.g., x/16w 0xc00000 to examine 16 words in hex, allow you to view raw data at specific addresses. You can inspect CPU registers with info registers to understand the processor's current state. Navigating function call chains is simplified with BT, backtrace, which provides a full stack trace. For pinpointing elusive bugs, conditional breakpoints such as b function if condition only trigger when a specified condition is met, while watch variable will halt execution whenever a variable's value changes. Furthermore, GDB's powerful Python scripting capabilities can automate complex tasks, like dumping custom kernel data structures, greatly streamlining analysis. In conclusion, effectively debugging kernel modules requires a strategic blend of both printf and remote GDB/OpenOCD techniques. Printf remains an excellent choice for initial diagnostics, simple status updates, and logging non-critical events due to its low overhead and ease of use. However, when faced with intricate bugs, race conditions, or hard-to-reproduce issues that demand interactive investigation, remote GDB and OpenOCD become indispensable. A recommended best practice is to always start your debugging efforts with printf for quick insights, and only escalate to the more complex GDB/OpenOCD setup when printf proves insufficient. Remember to always apply incremental debugging, back up your configurations, and thoroughly understand your target hardware specifics. Kernel debugging is a challenging yet rewarding endeavor that demands patience and a systematic approach. Mastering these powerful tools will profoundly enhance your ability to develop robust, secure, and highly reliable kernel modules.